Yes, it's visible.
Good evening, ma'am, and good evening, everyone present here. So today our presentation is based on diabetic retinopathy detection. First, I will be giving a brief introduction about just a second. I will be giving a brief introduction about what diabetic retinopathy is, what are the challenges when detecting this disease,
Your
and
voice is not clear. Is this
ma'am,
Anisha or Sucharita speaking?
ma'am, this is Anisha.
Yeah, so there is a slight echo, and your sound, your voice sounds like it's far off.
Ma'am, is it okay now?
Better, but yeah, go ahead.
Okay. I would start by giving a brief introduction about what diabetic retinopathy is, what are the challenges when detecting this disease, and our approach towards this problem. Next, I would move on to discuss a bit about the data that we have considered for our experiments and the various pre-processing steps that are related to it. My teammates would further carry the discussion regarding the methodology of the experiments and the results that we have obtained from it. So to begin with, diabetic retinopathy is an ophthalmic disease. That is, it is an ailment caused in our eyes. This disease mainly damages the blood vessels in the retina. So like any other diseases, this disease too has various stages. If detected at an early stage, then the disease can prevent a person from impaired vision or even complete blindness. Here, for detection of DR, colored images of the retina showing the blood vessels are used. But detection of this disease by trained physicians is not a very effective way, as it is more error prone, costly, and time consuming. Hence, computer vision techniques are used for its easy detection. However, a major challenge in these techniques is to encode the underlying complicated features and detect DR, especially for its early stages. For example, as we'll see that there are two stages of DR, namely the normal and the mild stage, which near about looks visually similar. So it is very difficult to detect the mild stage somewhat. Next, we move on to the problem statement. The problem statement at hand is here to create a system or say a model which can perform a multi-class classification task on retinal images. Now, generally, diabetic retinopathy can be categorized into 5 stages depending on the severity of this disease. The stages are normal, which means that there is no diabetic retinopathy in the patient, mild DR, moderate DR, severe DR, and proliferative DR. As we'll see in the upcoming slides, that we have tried various approaches and implemented a handful of models. To conclude, we have also compared the results obtained from these approaches. Next, we move on to the data description. For our experiments, we have used the diabetic retinopathy detection dataset that is available in Kaggle. This dataset originally contains about 35,000 images, but out of these, we have taken 4,906 images for our experiments. We tried to use a larger number, but due to lack of computational resources, we settled with this number. So among these 4,906 images, we used 3,623 images for training and 1,283 images for validation. In this data set, there are total 5 classes of diabetic retinopathy, which are mapped to the target variable as follows. So normal or no DR is represented by 0, mild DR is represented by 1, moderate DR by 2, severe DR by 3, and proliferative DR by 4. So the below images here correspond to each of those 5 classes mentioned.
Can you like zoom in onto the images? It's not, the differences are not visible.
Yes, ma'am. Ma'am, is it fine now?
Yeah, so can you explain like to people? I don't know what is the difference between these.
So mainly diabetic retinopathy is detected by an accumulation of blood vessels, which generally grows in size, and it can be spotted as a red or black spot, which is caused by accumulation of blood vessels. So here in the normal and mild images, we can hardly find any difference, like I mentioned previously, and that is why it's very difficult to uh, just a second. That is why it is very difficult to differentiate between these two images. In the moderate one, we can see that there is slightly more accumulation, followed by the severe one, where we can see even more prominent blood vessels accumulated. And in the extreme case, which is the proliferative DR, there are like a huge section of the retina is covered with this black spot, and there are patches present. So this is the difference between all the 5 stages.
So you mean there is a swelling of the blood vessels?
It's not a swelling. It's just a kind of a lump or accumulation that is formed,
Okay.
which generally ruptures in the extreme stage, causing blindness.
Okay.
So this was all about the data. Next, we proceed to the data pre-processing part. We further observed that in this data set, there exists a class imbalance. Now, the imbalanced data set can lead to bias in the classification's accuracy, which is our end goal. To correct this, we performed random downsampling on the majority class and random upsampling on the minority classes. So this step would include samples. This step would remove samples from the majority class and add samples from the minority class with replacement, because again there are less samples present in the minority class, and this compensates for the imbalance existing in the data. So if the samples in the classes are equally distributed, then the network can learn the features properly. But in the case of unequal distribution, the network outperforms generally for the highly sampled class. Now, after performing this, the resulting train set contained 3000 images. So this was all about the data part as a whole. Now, Sucharita would discuss about the image enhancement techniques used.
Again, your voice is also far away.
Is it fine now?
No.
Hello? Now? Is it audible?
You are audible, but the voice is not clear.
Is it fine now?
No, I mean, barely audible.
Okay. Hello?
Just say a few sentences and we will.
Hello, ma'am.
This is much better. Yes.
Okay. Hello. Okay. So now we will discuss about the different pre-processing steps that we perform on the input dataset before passing it to the model. In the first pre-processing step, we resize each input image of dimension 3888 cross 2951 to 640 cross 640 by maintaining the aspect ratio to reduce the training overhead of the neural networks. So as we have used very few images, that is 4,906 images, so we use a data augmentation technique over here. Basically, we perform random horizontal and vertical flipping in order to enrich our data set. So this technique expands the small training data set by adding additional images, which are variations of the available images in our data set. So by training a model with a large data set containing both the available and the transform images, improves the performance, that is the accuracy of the model, and it also enhances the ability of the model to generalize. Lastly, before random flipping and rotation of the images, each image is mean normalized using the following mean and standard deviation to avoid feature biasness and to speed up the training time. Next, we move on to the image enhancement techniques that are performed for each of the models being trained. In the beginning, we simply train our model on the preprocessed image without enhancing any of the images. Then we move on to the histogram equalization. We apply histogram equalization on the pre-processed images. So histogram equalization is a image processing technique that is used to adjust the contrast of an image by using its histogram. To enhance the image's contrast, it spreads out the most frequent pixel intensity values or stretches out the intensity range of the image. Over here, we use a histogram equalization as certain images look washed out due to a lack of sufficient contrast. So in case of those images, the light and dark areas kind of blend together, creating a flattened image that lacks highlights and shadows. So by performing histogram equalization, we make the dark pixels look more darker and the lighter ones look more lighter. Next, we move on to Gaussian filtering. We perform Gaussian blurring by using a Gaussian filter. Uh, Gaussian filter is a low pass filter that is used for reducing the noise, that is to remove the high frequency components of the image by blurring certain regions of an image. The filter is generally an odd size symmetric kernel, which is passed through each of the pixel of the region of interest to get a desired effect. The size is generally an odd number because the overall results, so that the overall results can be computed on the central pixel. So thus in a Gaussian blur, the pixels nearest to the center of the kernel are given more weightage than those that are far away from the center. Also, the kernels are symmetric. So we have the equal number of rows and columns. Over here, we have used a 3 cross 3 kernel with standard deviation 1.5 for Gaussian filtering. Lastly, we combine both histogram equalization and Gaussian filtering to get better results. So this process is done in order to reduce the noise obtained from the process of histogram equalization from the images. Now, here we have shown some examples after performing each of the image enhancement techniques on the training images. As we can see that after applying the Gaussian filtering, the images has been smoothened out in distinct regions. So it reduces noise efficiently and but it blurs the edges significantly. So we have performed Gaussian filtering over here. Next, we move on to histogram equalization. So here are some of the few of the images on which we have performed histogram equalization. Here the images actually don't provide much information from, since most of the areas are blurry due to lack of contrast. So after performing the histogram equalization, we see that the images areas with lower contrast gain a higher contrast over here. And next, we have performed both histogram equalization and Gaussian filtering on the pre-processed images. So by using this approach, we see that the darker regions have become more distinct And so this helps in further classification of the images. Now, Tanuj will discuss about the architecture of the various models that we have proposed.
So I have just one question
Yes,
here
ma'am.
about this retinopathy itself. So the aim is to detect this dark region, or is it to detect the thickness of the blood vessels?
So the thickness of the blood vessels, the five classes depends on the thickness of the blood vessels. Like for the severe class, if the blood vessels are more
Hmm.
thickened and the if the rupture is there, then it classifies it into the severe class. In case if the blood vessels are not as much as thick or as thin, then the case is like normal or mild. And in the moderate stage, the rupture is into the deeper layers and um, form a hemorrhage over there.
Hmm.
So the
Okay.
thickness and the hemorrhage both determines the type of the class of the diabetic retinopathy.
Okay. Thank you. Go ahead.
Yeah. Hello, ma'am. I hope I am audible. So I will be continuing with the model architecture. So in this project, we propose the following four architectures for the above mentioned problem statement. We start with inception V3, which has a total trainable parameters of 12245, followed by VGG16 with 20485 trainable parameters, ResNet 15 with 10245 parameters, and DenseNet 121 with total trainable parameters 7978856. Finally, we use an ensemble model of all of the four models mentioned above. We have used pre-trained weights for all of these networks. This provided us an advantage over training these large networks from scratch. This is an example of the model architecture inception V3. As we can see, there are convolutional layers, average pooling layers, max pooling layers, followed by dropouts, fully connected layers, and finally a softmax layer. This is an example of model architecture DenseNet 121. So basically, again, it follows a similar architecture, that is a convolutional layer, followed by a pooling layer, then a dense block. And as we can see, there are some resonant, like residual network-like structures as well, followed by a pooling layer, fully connected layer, and finally an output. Other details. We have used categorical cross-entropy laws, as this is a multi-class classification task. We have also used exponential learning rate scheduler. We have not used a single learning rate scheduler. Rather, we have used a learning rate scheduler, which is used to update the learning rate as the model parameters reach optimum levels. We have tried both stochastic gradient descent and Adam optimizer, but the latter showed best results. Talking about the ensemble model architecture, we start with an input image of size 640 cross 640. We pass this image to an ensemble of all these four models, that is Inception V3, VGG16, Resonant 50, and DenseNet 120. Each of these models predict the label of this image. And finally, we tag this image, the label, which is a combined voting decision of all these models. And hence we reach an output for a particular image. Next, I'll be walking through the code implementation of this project. I hope my screen is visible. So,
Your presentation is visible.
oh, okay, yeah. So we start with importing the libraries and utilities. We have used
Can you
Python.
zoom in slightly because it's very tiny?
Yeah, sure.
Yeah, that's better. Yes, yes.
So we have used PyTorch backend for this project. Along with that, we have used computer vision packages like OpenCV for performing various preprocessing tasks. We start with the data set. We have used the data set as mentioned before from Canvas. From there, we try to create a smaller, we have created data frame which contains the following information like image, name, level, that is, it indicates the degree of the diabetic retinopathy.
Tanuj, don't keep changing that side. Can you just fix one side and
Fix
don't keep
one.
zooming in and out?
Oh, okay, okay, sure. I'm zooming out a bit because I need to scroll down.
Yeah, so like find a midway that works
Sure,
for you.
sure. Yeah. Okay.
Yeah, please go ahead.
So, yeah. So, and patient ID followed by the path of the images where the images are stored, whether the particular image exists or not, because we mentioned that the data set is around original data set is around 35,000, and from there we have chosen nearly around 4,000 images, and which eye. So basically, this data set contains images of eyes, both left and right. So that's how we have categorized this entire data set into this data frame. Next, we plot the images for each of these classes as we have shown in our slide, that is normal, mild, moderate, severe, and extreme case. We have previously spoken about the data imbalance that we see in this dataset. As we can see that there are equal number of left and right eye images in the dataset. However, that is not true for the column level, right? So we see that the normal case, that is where we don't have any diabetics, that has the maximum number of instances compared to other classes. So as a result of this skewness, our results might be biased. That's why we try to balance the distribution of the training data set. We oversample the minority class and downsample the majority class. And we reach a consensus among the classes where each of these classes, that is 0, 1, 2, 3, 4, have equal number of images in the data set. Next, we define our model. So basically, we have started with the inception V3 and the pre-trained architecture. So that is why it's pre-trained equals to true. We have used a dropout layer with dropout percentage 0.1, probability error 0.1. So basically 10% of the neurons are randomly dropped each time, followed by a fully connected layer of dimensions 2048 cross 5. So this is of keen importance that Inception V3, uh, original Inception V3 has number of output features as 1000. So it can predict up to 1000 classes. But since in this case we need to predict just 5 classes, so that's why we overwrite rather the fully connected layer that I had previously shown in our website, and we overwrite it with output features as 5. So now the model is capable of predicting 5 classes instead of 1000 classes. We have used Adam optimizer and learning rate scheduler, that is exponential error, and the loss criteria that we are trying to minimize here is the cross entropy loss. So as you can see, this model has around 10245 parameters. We perform the following pipeline of transformations, which we term as the baseline data. We start with resizing each of these images. So each of these images are very large. They are around, on an average, they are around 2000 cross 3000 uh, pixels. So we have resized each of these images to 640 cross 640 as Inception Weekly, and all the other models perform best in this dimension, followed by random horizontal and vertical fill. These transformations make the model robust to such transformations in case in future someone gives adversarial sample or something like that. Followed by normalizing each of these images to avoid biasness. We have used batch size 32 in this case, and these are some of the examples as you can see the training data set of various degrees of severity. So as you can see, severity is 0 or severity 1. The blood vessels are comparatively thinner and the hemorrhage is hardly noticeable compared to say severity 4 or severity 3, where it's quite evident that there is something wrong in this patient. So I've trained these models, then we have saved the model weights for future use. Next we perform Gaussian blurring. Again we resize the images, followed by random horizontal flip and vertical flip. And next we use low pass Gaussian filter of dimension 3 cross 3 and the default sigma, that is the variance. this is an example of how what Gaussian blurring is doing. That is, the edges are smoothened out and it works on each of these pixels. We have trained this model and saved it like this. Next, we perform histogram equalization. This time, again, we have followed the same steps, but now we have used a histogram equalization technique in PyTorch called random equalize. And we these are some examples. As you can see, that that histogram equalization has like enhanced the image to a great degree. And for example, this image, if you observe carefully, you can very clearly see the veins. And the hemorrhage is also clearly visible. So definitely histogram equalization and these pre-processing techniques are necessary to make these images more interpretable to the convolution. And finally, we have performed histogram equalization plus Gaussian blur. So literature says that on histogram equalization, we sharpen the image, and if after that we use Gaussian blurring, Gaussian smoothing, so we try to smoothen out the errors in that normalization, right? So we have used this pre-processing technique as well in our project. So as you can see the pipeline, we have started with three sides, followed by random horizontal and vertical flip, then histogram equalization, Gaussian blur. Here we have used Gaussian blurring of the filter is of size 3 × 3 and sigma is 1.5. We have chosen batch size to be 32 and even 16 in some cases because due to lack of computational resources, we had to load the data somehow. Taking a smaller batches helps us in doing. Now next we visualize these images. As you can clearly see that the image is greatly enhanced and smoothened to a great degree.
Yeah, so my guess here is that Gaussian blur is being applied first to remove noise rather than smooth the
Ah,
edges.
yes,
It will reduce noise so that your histogram, is better reflecting the important characteristics of the image.
right. Next we
Yeah, I
train
should
them.
keep some of these images actually for my course. These are really
Sure.
good images.
Sure.
Yeah, please go ahead.
Yes. So we have trained the model again in similar fashion. Similarly, we have done the same things for VGG16. Same processes again, the Gaussian blurring, histogram equalization, DesNet 50, and DenseNet 150. Finally, we use the ensemble method. That is, we load all these pre-trained models and we try to generate for say for a given particular image, we try to generate the predictions for each of these models, right? And on the basis of a majority, we try to classify the image based on that. Say we have a impasse that each of these models predicts a different class. Then in that case, we give priority to that model which has shown the better accuracy compared to the others in individual cases. So that's how we have implemented the ensemble model part. Next, we'll be moving on to the results. So we have plotted the accuracy of the various models discussed above versus the image enhancement techniques. Uh, as we can see that Inception V3, uh, it has the lowest number of parameters, and as a result of which, uh, it has shown an increasing performance in baseline Gaussian filtering, histogram equalization, and finally the combination of them. Similar patterns are observed in VGG16, ResNet 50, and DENS 121 and on. Also, we observed that the state-of-the-art results in compared to all of these models was obtained from Ensemble, which has outperformed all of these models, and histogram equalization and Gaussian filtering have performed the best in this case. around 92.1% accuracy. The important thing is we have used the metric accuracy in this case. Histogram manipulation has performed better than Gaussian filtering, and Gaussian filtering has performed better than the baseline. Thank you. This was our presentation detection of diabetic retinopathy. Definitely, there are more advanced. We can definitely find more advanced ways to detect.
So, Tanuj, your voice is not clear.
Yeah. So I was say. As I discussed the results, that ensemble method has performed the best compared to all the other architectures, and especially the histogram equalization plus Gaussian filtering combination has performed the best. So together, if we use this ensemble method and the histogram equalization and Gaussian filtering, we get the state of the result of 92.1% among all of these models. We have also observed that Gaussian filtering has performed better compared to the baseline values. Again, histogram equalization has performed better than Gaussian filtering, and histogram and Gaussian filtering combination has performed better than each of these cases. So definitely there are better architectures maybe to detect diabetic retinopathy, and we hope that we can find such methods and use other image enhancement techniques which can outperform the current ones and give us better results. That's the end of our presentation.
So right now, this is the state of the art, or this is just one?
So like among all our models, this was the best, 92.1%. But people have used larger networks which have around accuracy of 97% to 98%.
Okay.
But those architectures are really big, so we couldn't implement them.
No, that is fine. I just wanted to know what is the state of the art.
So that's around 97 to 98% roughly. And
Mhm.
among all our models, we found 92.1% to be the best in our case. That's
Thank
the
you.
end of
Yeah, thank you. So that was a interesting talk. Does anybody have questions or comments? Okay. So what I would like to ask is, so you have these 5 different classes, right? And this is multi-class classification.
Right. Yeah. Yes, no.
So yeah, I guess maybe my question is sort of submerged in this. So I was only wondering between normal and mild. So in the beginning, Sucharita said it's difficult to distinguish between
Right.
these. Did she mean just visually, or are there problems in this detection? Sir?
Yes, ma'am. So we went through some of the literatures, and there they mentioned that they had performed some experiments, particularly on the normal and mild DR cases, and then they didn't find really impressive results. So that is one point of improvement we can even consider for ourselves.
Okay. All right. Yeah. So I don't have any other questions.